in real life, one of the reactants is probably going to run out before the other one does, unless you carefully plan it. That reactant that runs out first is called the limiting reactant, and it gets that name because it limits how much product can be formed. Here's a non-chemical way of understanding this. Imagine that you're making brownies and you're using a mix, so every box of mix can make a batch of brownies, but it requires that you add an egg. So let's say you look in your kitchen and this is what you find. You find that you have 10 boxes of mix. Well, with 10 boxes of mix, you should be able to make 10 batches of brownies. However, you look in your refrigerator and you find out that you have only 6 eggs. Since you need an egg for every batch, you're limited to only 6 batches of brownies. You can't make any more than that. Even though you have plenty of mix, the eggs are the limiting reactant in this case. When you're done with the reaction, you're going to have some reactant left over. It's not the limiting reactant because that ran out. That's what stopped the reaction. The reactants that remain when the reaction is over are called the excess reactants. Going back to the brownie mix, the brownie mix is the excess reactant. We have 4 excess boxes of brownie mix. Now let's apply this to chemistry. Let's say we have this reaction here. This is ammonia reacting with oxygen to produce nitrogen monoxide and water, and it's balanced here for us. The question is this. I have 30 grams of NH3 and I have 40 grams of oxygen, and I want to know how much NO will be produced. Well, this is a more complicated problem than we've encountered before, because if I start out with 30 grams of ammonia as my starting point, I might get a different answer for how much NO gets produced than if I started out with 40 grams and determined how much NO gets produced. So let's have a strategy for solving this kind of a problem. The first thing you want to do is use stoichiometry to compare one reactant to the other, just like we've been doing. So here's what I know. I have 30 grams of ammonia, I have 40 grams of water, and I want to know ultimately how many grams of nitrogen monoxide are going to be produced. As I just said, the first thing I want to do is compare one reactant to the other using stoichiometry. So I'm going to choose ammonia as my starting point. It really wouldn't matter which one I had chosen. 30 grams of ammonia. By comparing the reactants, what I mean is I want to find out how many grams of oxygen is it going to take to react with that 30 grams of ammonia. Well, I can't cross the Grand Canyon without using the mole bridge, so I need the molar mass of ammonia. I look it up. Nitrogen and 3 hydrogens, add them all up, I end up with 17.031 grams per mole. By using molar mass in this way, I now have moles of ammonia, and I can apply my mole ratio. According to the reaction, there are 4 moles of NH3 needed for every 5 moles of oxygen. So now moles of NH3 disappear, and I have oxygen in my answer. But I don't want moles of oxygen, I want grams of oxygen, so I can compare it to the 40 grams that's up here. Well, this is oxygen O2, and that makes a difference. When I look it up on the periodic table, a mole of O is 15.999, so a mole of O2 would be double that, and that ends up being 31.998 grams per mole. With moles canceled out, I'm now going to get grams of oxygen. So then I do my calculation. The answer is 70.46 grams of oxygen. So here's what that's telling me. It tells me in order to use up the 30 grams of ammonia, well, here's what I do with that information. I compare the needed amount that I just calculated with the available amount that the problem tells me I actually have. So looking at this situation, my calculation told me that I need 70.46 grams of oxygen to use up the ammonia. But I only have 40 grams. When I compare the 70 grams with the 40 grams, clearly I don't have enough oxygen to complete this reaction. So that's what this means. Oxygen is the limiting reactant. That's the limiting reactant. When 40 grams of oxygen are used up, this reaction is going to stop because I'd need 70 grams to use up all the ammonia I have here. Okay, now that I know what the limiting reactant is, I can go on to answer the question. My starting point now I know has to be 40.00 grams of oxygen. And then I can answer the question how many grams of NO are produced by using ordinary mass-to-mass stoichiometry. First step is change to moles. 31.998 grams per mole. Now I do a mole ratio, 5 moles O2 for every 4 moles NO, and then I do a second molar mass to get NO grams. The molar mass of NO turns out to be 30.006 grams per mole. And let's just double check our units. Grams are gone, oxygen moles are gone, moles of NO are gone, and I have grams of NO. That's what I want. So now I just do my calculation. Should have 4 significant figures in my answer, and it turns out to be 30.01 grams of NO. Let's try another one. It says here if I have 5 kilograms of aluminum reacting with 5 kilograms of iron 3 oxide, which is the limiting reactant? And the balanced chemical equation is given here. Okay, here's the setup. Here's our balanced chemical equation up on the top, and the problem is asking me if I have 5 kilograms of aluminum and 5 kilograms of iron 3 oxide, which is the limiting reactant of these two? Well, I don't have to actually find a product here, but I do have to compare these two to find out which is the limiting reactant. I'm going to choose Fe2O3 this time, just to show that you don't always have to pick the first one as your starting point. So starting out with 5.00 kilograms of Fe2O3, I want to determine in kilograms how much aluminum will be needed. Well, I can't cross the kilogram canyon without using the mole bridge either. So probably first I should convert kilograms into grams so I can use molar mass, because molar mass is always in grams per mole. Well, 1 kilogram we know is equal to 1,000 grams. So I can change kilograms into grams. Now I can use molar mass. The molar mass of Fe2O3 is 159.691 grams per mole. Now grams cancel, and I have moles of Fe2O3. Here comes the mole bridge. 1 mole of Fe2O3 reacts with 2 moles of aluminum. With the moles and the Fe2O3 gone, now I have 2 moles of aluminum. I'll have to change that into mass because ultimately I want kilograms here. The molar mass of aluminum is 26.982 grams per mole. So now I've converted to grams of aluminum. And then one more step, there are 1,000 grams per kilogram. With grams canceled, now I have kilograms of aluminum, and that's what I'm trying to find. Let's do the arithmetic. When you do the arithmetic, to 3 sig figs, you end up with 1.69 kilograms of aluminum. Okay, which is the limiting reactant? Well, this calculation told me to use up all the iron, I'm going to need 1.69 kilograms of aluminum. When I compare that with how much aluminum I actually have, I have way more aluminum than I need. So I won't run out of aluminum. Instead, I'll run out of Fe2O3, which means it is the limiting reactant for this problem. Future one. This is saying if 20 grams of sodium react with 20 grams of chlorine, how many grams of sodium chloride will be produced? And the balanced chemical equation is given for you. Well, here's your starting point. You've got 20.0 grams of sodium. You also have 20.0 grams of chlorine, and you want to know how much NaCl is going to be produced. Since you have information about both reactants, you have to first determine which one's going to run out first, which is the limiting reactant. Let's do that by comparing sodium to chlorine. I'll start out with 20.0 grams of sodium, and I'll use stoichiometry to determine how many grams of chlorine is it going to take to use that up. The first thing I need to do is use molar mass of sodium to change from grams to moles. Sodium is 22.99 grams per mole. That cancels grams and gives me moles of sodium. Now comes the mole ratio. 2 moles of sodium I want to put on the bottom so I can cancel that. 1 mole of Cl2 I want to put on the top, so that ends up in my answer. Now moles in sodium drop out. I have moles of chlorine. What I want is grams of chlorine so I can make a comparison, so I'll multiply by the molar mass. For every mole of Cl, it's 35.453, but this is Cl2. So be careful on these diatomics. Make sure you double the molar mass in the stoichiometric calculations. So 35.453 doubled is 70.906 grams. With moles now canceled out, I'm going to get grams of Cl2. The answer to 3 significant figures is 30.8 grams of Cl2. What does that mean? I need 30.8 grams of Cl2 to use up all the sodium. I only have 20. So that makes chlorine the limiting reactant. Now that I know that, I can answer my ultimate question of how many grams of sodium chloride are going to be produced. Starting out with my limiting reactant, 20.0 grams of Cl2, I want to end up with how many grams of NaCl will be produced. The first thing I have to do is change grams to moles. So 70.906 grams goes on the bottom and 1 mole goes on the top. That gives me moles of Cl2. The mole ratio is 1 mole of Cl2 for every 2 moles of NaCl. This cancels off my moles of Cl2 and leaves me with moles of my product, but I want grams. So I'm going to use the molar mass of NaCl, which is 58.443 grams per mole. Now moles are gone, grams of NaCl is my unit, and I just do my arithmetic to get my answer. To 3 significant figures, this answer comes out to 33.0 grams of sodium chloride.